All right, so page 78, 5 through 8. All right, so the reaction on page 78, number 5, I think, is aluminum and bromine, correct? Yes, producing a compound. All right. So let me just get there really fast here. All right. So here we go. We have a little chart. We have before and after. So we have aluminum. What's the symbol for aluminum? What about bromine?
BR.
Close. Not BR.
BR2.
BR2, thank you. It's a Hunkelbrief. It forms aluminum bromide, AlBr3. That is a compound. Okay. Now, you maybe didn't know that, but sometimes with these problems, if they're giving you reactions, it helps to write it out. Even if you don't know the symbols, you can write the words. You can write aluminum plus bromine yields compound. Why? Because it just helps you visualize it. All right, so we have before and after. Before and after. So before the reaction, we have 10.3 grams of aluminum, and then 0 after. So 10.3 grams and 0 grams after. What does that mean?
It washed.
How much of the aluminum reacted?
All
All of it. Good. Bromine started with 100 and then ended with 8.5. 100 grams, 8.5 grams. Caitlin, what does that mean? If we started with 100 and ended with 8.5. Did all the BR2 react? No. Good. How do we know that?
Because it's not 0.
Very good. It's not 0. There's some left over. So this is called the excess. This is called the limiting. Limiting is always reacted 100%. Excess, there's some left over. You don't really need to know those words, but that's what that's called. And the compound before, obviously, is 0. And then afterwards, does it give us? No, you have to figure that out. Okay. All right, so first question here on number 6. Not number 6, number 5. How many grams of bromine reacted? Who can tell us that? How many grams of Br reacted? 91.5 grams. Very good. So if you start with 100 and then 8.5 is left over, subtract them. 91.5 grams is actually in the compound. And we know all 10.3 are in the compound as well, because 0 is left afterwards. So when you add these together, that's the mass of AlBr3, the compound. So the answer to 5, the second part, is, where the heck is it? 101.8. 101.8 grams, because that's these two numbers added together. Conservation of mass. Mass of reactants, this one and this one, have to equal the mass of the product. This is extra. It doesn't matter. It doesn't react, so it's not part of the deal. It's extra. Okay, that's that one. Next, number 6. All right, is this water?
Yeah.
Okay,
No.
are we separate? No?
Yeah.
Yes,
Water.
separating water. Okay, so we have H2O going into H2 and O2. So again, like that question I was doing with Riley, I put a 2 here and a 2 here. That's just balancing it so I have the same number of atoms. 4 H's, 4 H's, 2 O's, 2 O's. That has nothing to do with the number of grams in this question. All right, 6. We have 10 grams of hydrogen and 79.4 grams of oxygen. 79.4 grams, 10 grams here. How many grams of water did we start with? Adriana. Hey,
89.4.
focus. Say it again.
89.4.
89.4, very good. All we do is add that together. 10 plus 79.4, that's how much we started with here, because conservation of mass, reactants equal products. That's how we do number 6. 7, this time we have sodium and chlorine. All right. So sodium and chlorine. What's the formula for chlorine?
CO2.
Cl2, diatomic, good. Forms NaCl, we need 2 of those and 2 of those again to balance it. All right, question says we have 15.6 grams of sodium. So 15.6 grams here. And how many grams of sodium chloride? 39.7. 39.7 grams. How many grams of Cl reacted? Willow, what do you think? Number 7 here. Say that again?
I think I read you the wrong number.
Okay.
You don't know if I have the right one.
All right, that's fair. So how would we solve for the amount of Cl2?
Will you just subtract 15 from...
Oh, I'm asking Willow. Let's see what she says.
I'm thinking maybe subtract 15 from 39.7.
Right, 39.7 minus 15.6 gives us that number. Who has that number?
24.1.
24.1. Very good. 24.1. Why does that work? I'm going to sound like a broken record. Because conservation of mass. Mass of reactants equals mass of product, so that your scales, right, the scales are balanced. All right. How much sodium reacted? All of it. 15.6. That's kind of a bad question there. All right, number 8. Now we have magnesium and magnesium oxide, or magnesium and oxygen, and it makes MgO. I need 2 of those and 2 of those. Okay. This time we have 10 grams of magnesium and it forms 16.6 grams of MgO. How many grams of oxygen reacted, Andrew? If the product is 16.6 and magnesium is 10 grams, 6.6, right, 6.6 would be the grams of O2. Again, conservation of mass, reactants equal products, so that's 16.6 on both sides. Questions on those? Okay, so that's number 8 there. All right, 79.13. I'm just going to read the answers to A and B. A, 58.44. I think that's what Willow read me. Is that what you read me last time?
I think so.
Yeah. So 58.44, you're just adding them together, I think. B, you're subtracting those two numbers and you get 66.7. That's for 13B. 14, we already did that. I didn't mean to assign it again, sorry. But the answer is the appearance can change and it's a physical change, so the friend is wrong there. All right, 96.83. All right, so what do we have? Phosphorus, and we have hydrogen. That's not it. H2. We get PH3. We need 2 of those, 3 of those, and 2 of those. All right, we have before and we have after. All right, so here we go. Phosphorus combines, let's see, 123.9 grams of phosphorus. So we have 123.9 grams of phosphorus. And it says after the reaction, all right, what are we producing? Sorry, 129.9 grams of phosphine. So after 129.9 grams, 0 to start because you can't have anything before you react. 310 of H2 remains. All right, here's my questions. How many grams of phosphorus reacted? How many grams of hydrogen did we actually start with? So how are we going to answer all of these questions? What was the mass of hydrogen used? Let's figure this one out first. Mass of hydrogen that actually is in here. Here's the hint. This is excess that's left over. This is limiting. So who remembers what I said about limiting?
I don't remember any conversations.
Nothing? If this is excess, there's some left over. There's always 2 reactants. One of them is called excess, one of them is called limiting. You do not need to know those words, but you need to understand this concept. If this one is limiting, that means it runs out. Doesn't have any left. So what do I put here? 0. So that's how we can answer this question. How many grams of hydrogen actually reacted? If all of this is used, all of that is used to make the product. So all of this is right here.
There's no more left.
There's none of this left, right? But how much hydrogen did we use?
6 grams.
6 grams. That doesn't go in for the question mark, but 6 grams of hydrogen actually reacted. How'd you get that?
What? That's the
Right.
129.
123.9 plus 6 equals that number. So that's how many grams of H2 actually reacted. Mass of reactants, right? These two added together have to equal products. That's balancing equations. That's conservation of mass. Here's the last question with this one. What did we start with for hydrogen? If we ended with 310 after it was over, this is left over, didn't react. Trevor, what's the starting amount of H2? 316. Very good. 316. Kieran, what's going on over there?
I dropped something and I went to pick it up, and now I'm going back.
Seems a little dramatic.
What was I supposed to do? Pick it up?
Yeah, probably. You with me here?
I'm following.
Good. 316 because 6 grams reacted, leaving 310 left over. That was kind of a hard problem. All right, last one. Well, technically number 3 is the last one, but that's multiple choice. Okay, 84. Great question. All right. If we have H2 plus O2 creating water, and we have 100 particles of O2, 100 particles of H2, how many particles of this do we make? And then which one do we have left over, and how much do we have left over? Let's scale it down. Instead of 100, let's just do 5. Now let's do 4. We'll do 4 particles instead of 100. And then we can just scale it up.
That's a big difference.
Yeah, but we can just relate it to the question and get the answer that way. So we have 4 H2. Make sure you're paying attention up here. And 4 O2. All right. Amanda, how many H's do I need to make 1 water? How many H atoms, hydrogens, do I need? Not H2, hydrogen atoms. So each red one. How many of these do I need to make 1 water? 2. How many oxygens? So just one of these yellow ones. How many of these do I need to make 1 water? How many of these to make water? I'm not trying to confuse you. If I am, let me try again. So I have, forget these 3. Let's look at this one and this one. Do I need both of these to make a water molecule?
Yeah.
Okay. Do I need both of these to make a water molecule? No. How many do I need? Just 1. I need 1 oxygen, and I need 2 H's. That's H2O, and there's our Mickey Mouse. With me now?
Yeah.
Good. So if I keep doing this, will all of the, and this is for everyone to think about, but I'm still talking to Amanda. So I keep doing this, will all of the hydrogen be gone? Will all of the oxygen be gone? No. Good. So if I take 2 more, and this one, make water. Take 2 more, and one of these, make water. Take 2 more, make one of these here. Take one of those to make water. How many are left over? 2 out of 4, which is half. So however much oxygen we start with, we'll always have half of it left over. Why? Because you only need half of them to make water, because it's only 1 oxygen. So it's 2 for every 1. So 2 to 1. That's why all the hydrogen is gone. It uses all of it because you need both. So go back to the question. What's the answer? How many waters can we make if you have 100 of O2 and 100 H2? Morning. If I have 100 H2 and 100 O2. So I did the example with 4. So scale it up to 100. Let's say I had 100 of these and 100 of those. How many of these can I make? I started with 4 molecules, right? And 4 here. So 2 are left over, but all of these are gone. So hold on. If I have 100 here, how many would I have here?
150.
Maybe if I do this, it'll help. I don't know. Maybe not. So I started with 4. You got this. You got this.
Jeez.
Hey, stop it. You got 4 here that I had, and now those 4 are right here. 1, 2, 3, 4. Those are your H2s, right? So all the hydrogen's gone. So if I have 100 here, or I have 1,000 here, or I have 2 million here,
That's a lot.
all of these will always be gone because you need 2 H's to make 1 water. So if there's 100 here, how many of these do we make? All of them, 100, thank you, very good, 100. Now, here's the next question. How many of these are left over? If there was 100 to start. Very good. Is that what you meant when you said 150?
Yeah.
Very good. So, the answer to the homework is 100 water molecules and 50 oxygen. it's not that easy to understand when you're just reading the question, but if I show you with the magnets and you draw it, it should be a little bit easier, okay? So it's not that easy of a problem. Good job. So 100, you would make 100 water, and you'd have 50 oxygens left over. And if you look at the balanced equation, everyone look up here. When you balance this with those big numbers called coefficients, what's the ratio between H2 and H2O? 1 to 1 or 2 to 2, right? So if you have 2 of these, you'll make 2 of those. If I have 1 of those, I'll make 1 of these. If I have 5 of those, I'll make 5. So it's a 1 to 1 ratio where this is 1 to 2. So it's always going to have some left over. You don't need as much. Okay, number 3 on 98. Answer is conservation of mass, wherever that is, C. C. The answer is C. All right, put those books back, please, in an orderly fashion. Take out your notes. All right. Yesterday I had you feel this thing before and after. What happened? Got hot. And I said write down how it, hold on, they're helping me out over there, so I'll wait. Good work.
Thanks.
All right. So it got hot, and I said write down how this proves the law of conservation of energy. So that's what we're going to write right now. Law of conservation of energy. And who looked up the definition? Almost all of you did. So who wants to read me what they wrote?
Energy cannot be created or destroyed, only transferred.
Energy cannot be created or destroyed, only transferred. Good. Only
I did
transferred.
not write
And I still only think there's one R, Hanukkah, but if there's 2, then I'm wrong. You did? Yeah, go ahead real quick. All right. Who said they did not get that? Someone just said I did not
No,
get
she
that.
said she couldn't write today.
Oh,
That's a Mars.
got it.
Oh.
Wait, did you get that from Google?
Yes.
It's not the scientifically spelled.
So anyways, energy cannot be created or destroyed, only transferred. So, in the example here, how does this prove energy being transferred, Jake?
Heat wasn't created, no more heat was created.
The heat, okay, where did the heat come from? Good question, good answer. The heat came from the chemical energy inside here. So that's kind of hard to understand right now, but a lot of things have energy. Right now, this paper doesn't feel warm, but if I light it on fire, will it be warm?
Oh, yeah, like
It's not just from the fire.
The fire.
It's not just from the fire. 'Cause the fire doesn't have this to burn, it won't produce fire, it won't produce heat.
Gas.
Gas or something else you need
What are you?
Oxygen.
besides that.
Something to burn.
What's that called?
A fuel.
Yes, fuel. So when you burn something, paper, wood, oil, coal, natural gas, whatever it is, the fire is getting energy from what it's burning. Fire doesn't just make energy on its own. So anyway, the energy is coming from inside here. We'll talk more about that down the road. But where does the energy go? So I'm holding it right now. It's really hot. Goes into my hand and into the air. That's how you are explaining, hopefully, what you wrote. I didn't go through it with you, but that's how you're going to write, not how you're going to, how you did write, hopefully. The law of conservation of energy is shown through that. So energy cannot be created or destroyed, only transferred. Energy from a hot pack goes into your skin, or hand or arm, whatever you want to put, from a hot pack goes into your skin and into the air. Because the air It's definitely not as hot as that hot pack was yesterday. It's not hot right now. But. Was this a chemical or physical change?
Yes.
I'll give you a hint. If I put this whole plastic thing in boiling water for about 10 minutes, take it back out, it goes back to the way it used to look. So does that help at all? It's physical. It's actually just dissolving and undissolving. That's all this is. When you snap that little coin, what it does is it agitates all the dissolved particles, which are these white things here, the white stuff. It's called sodium acetate. When you put it in boiling water, the water's hot enough inside here to re-dissolve it. So this is just dissolving and then precipitating. Dissolving, precipitating.
So you can reuse those?
Yeah. Like, I bought this a long time ago. I just keep using it over and over and over. I'll keep using it until it probably get a hole in the bag eventually. But yeah, you can reuse it. Does anyone have hot packs or cold packs at home you can reuse? Similar concept? The cold pack you just put in the freezer.
How did you reset that little coin thing in there?
Well, you don't. You just bend it a different. So I bent it a little bit, and then I'll just bend it again. So it's not like any special reaction going on with that. It's just bending it irritates the particles. Think of it that way. Do you have a hot pack that does this? One of these, yeah. So it's a physical process. Physical. Who thought it was chemical because the color changed? Almost everybody, probably. That's what I taught you. But what you didn't know is that sodium acetate, before it was dissolved, is white. So this didn't change color. It's the same thing. You just didn't know that because you couldn't see it. So yeah, this was a physical process. When the kids say, wait a second. Anything that gives off heat, I thought is chemical. You can give off heat when you dissolve something or when something becomes not dissolved. Heat can be released or absorbed. As long as what doesn't change, it's still physical. The composition, and it's the same chemical. It didn't change. You have to take my word for that because we're not doing any tests to prove it, but this is the same chemical, so it was a physical change. So sometimes energy transfer is a physical thing. In fact, most of the time, if I touch the board, guess what? It feels cold. That's not a chemical change. Okay, my hand is still my hand. It didn't turn into like a hook or something. All right. So yeah, this is a different kind of energy transfer. So this is hotter than my skin. The board is cooler than my skin. So where's the energy transferring there? From me to the board, right? So that's the important concept here. It's constantly being transferred. And what does it depend upon? Depend on, I should say. What does it depend on? What if I was the exact same temperature as this hot bag? Would there be any transfer of energy at all? No. So what does it depend on? Differences in temperature. And how does it always move?
High, low.
Right. Hotter to colder or warmer to cooler. So energy always moves, always flows from, I'm going to put higher temperature to lower temperature because it isn't always hot and cold. You could have something that's 0 degrees Celsius come in contact with something that's -10. The 0 will lose its energy to the -10. That sounds weird, but it would work that way. So it isn't always hot and cold. You guys ever go to the grocery store and open up the big freezer? But you're wearing maybe shorts or sandals?
Oh, it's cold.
You feel the cold air, but it's not on your feet. You ever notice that? You never feel it in your face. You feel it down. It hits your legs first. Why is that?
Hot air rises, cold air sinks.
Hot air rises, cold air sinks. Why is that?
Because it can.
Wow.
Because it can. We'll talk more about that.
I'll tell you what, I'm going to give you a solid answer here. Science.
Science, right. Okay, I'm going to write 2 words on the board. One on the left side, one on the right side. Copy them down. See if you know the definitions of them. Endothermic.
I remember it's exo.
And exothermic. And you need reference tables. Take those out, please. There's 2 types of processes or processes in life. There's the process that energy is given off, like this hot pack gives off energy, or if I took a cold pack and put it on my arm, the cold pack's taking in energy. So that's really the only 2 options with energy. You either lose it or you gain it. Who knows which word? Raise your hands. Which word means which one? Annika. Good. Exothermic. Releasing heat or releasing energy. Releasing energy. Anything that is exothermic, Autumn, feels to us. Feels what? Hot. Feels hot to us. This is important. If it feels hot to us, it's giving us heat. So it's giving it off. Endothermic is what? Taking in. I'm going to use the word absorb. Absorbs. Or absorbing. Just say absorbs, whatever. Absorbs heat. Actually, energy is a better word. Sorry. Absorbing energy. So what would that feel like to us?
Cold.
Cold. Feels cold to us. So again, if you're holding a cold pack, the energy is going from us into the cold pack, so that cold pack is absorbing the energy. It feels cold to us. I have a demo that I don't have time today, but I'm going to mix these two, and it's either going to get cold or it's going to get hot, and you'll tell me which process it is. It's just an example, so it's an obvious example. Okay? So yeah, exothermic, endothermic, two words that I was thinking of using for the word of the week, but I didn't. So anyways, table I is where we're headed to now. Table I, for a couple minutes here. Table I. Why would I be on table I right now?
Because it shows the reaction and the triangle H.
Triangle means delta.
Delta H.
Got table I? Working on it? Annika? I don't know. It tells us. Look at the wee way bottom.
Based on molar quantities represented.
What's it say at the bottom? Minus sign indicates exothermic. So, if you look at all those reactions on there, look at the right side underneath where it says delta H. Triangle means delta, which means change. So change in H means change in heat, which is energy. So if you look at the delta H, look underneath, see all those numbers. Look at the very first one. I believe the first one is negative 890.4.
Yep. Yes.
So that means that reaction gives off that much heat. If you keep going down, find the first one with a positive number. Is it 66.4?
182.6.
Okay.
Oh, you were close.
Close, right? Yeah. So those reactions with the positive mean they get colder, they take in heat. They take in that many, I think the unit is kJ, right?
Yeah.
Kilojoules, that's a joule is a unit of heat. We'll have to talk about all that this year. But that chart we're going to be talking about a little bit here, and it's appropriate because mole day is coming. And we need to learn about moles a little bit to look at that chart. But it's related to this. So there's only one of two things a reaction can do. It can absorb energy or it can release it. This chart kind of gives us a little help with that, at least for these reactions. Okay? So I'm going to stop there because the bell's going to ring. You don't have any homework because we didn't quite get to where I wanted to. Don't forget the quiz tomorrow, particle diagrams, and I will be after school tomorrow, not today. Oh, who's not going to be here Friday? A lot. So those of you who are here, we're going to do some just Regents review or Kahoot or something like that.
Kahoot, yeah. Let's do it.
Have a wonderful day.